All right. Welcome everyone to our Open NLP meetup. My name is Julian. I will be the moderator of tonight's event. And we have two talks scheduled for tonight. One is by Max and the other one by Vladimir. So the agenda for tonight is we will start with the talk by Max about interpreting 100,000 climate impact studies with NLP. The talk will be about 20-25 minutes. Then there will be 5 minutes for questions, maybe 10 minutes for questions. Then we will continue with a second talk. And after that, there will be again time for questions and then a Zoom breakout session where you can split up into smaller groups, get to know each other, introduce yourself to the others, and also discuss the talks, topics, and NLP in general. So this meeting is being recorded. So if you don't want to be in the recording, just keep your camera turned off. And if you have a question later on, feel free to post it in the chat. Otherwise, you can just raise your hand after the talk and then speak up. So now without further ado, let's start with tonight's talks. Let me introduce the first speaker to you, Max Callaghan. So Max is a postdoc at the Mercator Research Institute. And there he is working on sustainability research. And in this talk, I think we will see like an intersection of science, climate science, and also to some extent politics and also NLP. So I'm very much looking forward to this talk. And the preprint is online, publicly available. There's code publicly available. So it's a perfect fit for our Open NLP meetup. And yeah, without further ado, I would say, Max, the stage is yours.
Okay, thank you very much. And thank you for having me and for inviting me. It's a pleasure to be here. So I will try to share my screen. Okay. Okay, I hope you can all see my slides. Yeah, perfect. Yes. So it's my pleasure to share with you today some research that we did over the last couple of years, starting almost exactly at the time that COVID started, actually, and then finishing late last year. So this is really collaborative work with many colleagues from different institutes, from climate analytics, also in Berlin, and also from a climate scientist in NOAA in the US. And really we were climate scientists, social scientists, a couple of machine learning people, and really quite an interdisciplinary team working together on this application. So to set the scene, basically the IPCC, for those who don't know it, produce assessments of the evidence on climate change every 5 or 6 years or something. We've just had the latest round of assessments. It's 3 enormous reports on the physical science of climate change, impacts and adaptation, and responses, mitigation. And these reports are really enormous, and they contain tens of thousands of citations. And the reason why they're so big and they're getting bigger is because also climate change, the science of climate change is getting really, really big. So this graph is now just a tiny bit out of date, but basically what we can see is that in the first IPCC reports, we had a few hundred papers that we needed to be assessed. So the scientists could simply read those papers and assess them. And by the time of the 6th assessment report, we have hundreds of thousands of papers published in one assessment cycle. So it's not, you know, even with the huge amount of effort that goes in, and this is scientists volunteering their time, it's impossible to read all of these papers. So what we read and what we don't read gets more complicated. How we decide what we read gets more vital. And in the maps that we do, that we can no longer really account for the uncertainty about what is in the literature. So if we have only read a part of it and we say, okay, this is the science, these are the impacts that we've found, we're likely missing something, and what we're missing and how we account for what that might be is really tricky. But the way we kind of got inspired to try this study is that behind this map here of the impacts of observed impacts of climate change. So this is impacts that have already happened due to climate change. There's a big table which contains the kind of results of expert assessments of the scientific documents. And this tabular data is really interesting for us because it contains, we can go into these references, extract the text, and then we already have some labeled text, which is really nice. So basically what we decided to do was we're going to use, basically do supervised machine learning on this labeled data. And to do this, we eventually came upon using BERT and fine-tuning BERT or BERT-type transformer models to train, basically to identify the literature on observed climate impacts and to identify on what type of impacts this is and in which systems these are. So the process we did was we did a broad search in literature databases. We had to additionally do some hand screening and coding because there are only about 300 examples in AR5. Then we used supervised machine learning to predict the inclusion and impact type of the kind of hundreds of thousands of papers that we get from the query. We used named entity recognition to extract geographical locations of titles and the abstracts. And then we map these entities onto grid cells, and then we combine this information about observational data about the climate to kind of fill in kind of gaps from both types of data and say, come up with a kind of fuller picture of what we know about the impacts of climate change. And we can describe then evidence gluts and evidence gaps as well. So first on the search query is a tricky problem because we have not to scale, we represent here all of the literature, and some of that literature is relevant, and we want to capture that part of the literature. And some of the relevant literature is already identified in the last IPCC report. So we have some idea about what we want to capture. And ideally, we want to create a query that's a little bit like this box. So we capture all of the relevant literature with a small amount of the rest. But the thing is, we might, and we can test this by making sure we capture all of the identified relevant literature, but we might end up with a situation like this, which probably happens to us to a certain extent. I think we definitely miss some relevant studies. But what we can at least test is make sure that we don't end up somewhere like this, where we are also missing some of the literature that was identified already in AR5. So we came up with a big query, and I won't talk about it that much, but we just had a long list of keywords to do with climate impacts and kind of observations. And then we have this kind of labeling infrastructure that we built in the group kind of organically over the last 3 or 4 years, as we started doing what we call systematic review in the kind of scientific world, where we are trying to identify relevant documents and go through these systematically and label them. And all of these processes are kind of nicely amenable to the use of machine learning for kind of supplementing or complementing these processes. So in our labeling task, we had a large team of screeners. These were climate scientists mostly, mostly the author team. And we would screen these documents and we would say, okay, is this relevant to climate impacts? If so, what type of evidence is it providing? So is it directly attributing this impact to climate change, anthropogenic climate change? Is it just showing a trend and attributing this trend? And lots of different other categories. What system is this in? What are the drivers of this impact? And we really had a very detailed labeling task, which was quite challenging. And so when it came to developing the models, we wanted to, because this is rather sensitive, like the results of this are quite sensitive in some ways, because we're trying to say, okay, this is the literature on climate change. So we want to be quite careful about how we validate our models. And we ended up doing, in the end, quite labor-intensive or computationally intensive process of nested cross-validation to do this, where basically the idea is to separate the hyperparameter optimization from the estimation of performance. So I don't know if I can come back to this later if people are interested, but I think I won't spend time talking through exactly how this works. But basically, we just make sure that when we have a loop for optimizing the hyperparameters, and when we do the validation, when we estimate the performance of the best model, that's on a different test set to the validation in the that we're doing for optimizing. Okay, so the next piece of information that we want to bring this together with is evidence from quantitative detection attribution literature. So our co-author Tom Knudsen from NOAA, he developed a method for attributing trends in temperature or precipitation to human influence on the climate. And the way this works is we say, is there a trend in temperature, let's say, over the period 1950 to 2018? Is this trend significantly different with what a climate model would have expected without anthropogenic forcing, so without greenhouse gases and all of the other ways that humans influence the climate? And if so, is it in line with what a climate model predicts with anthropogenic forcing? And so if these conditions are all there, then we can say that this trend is attributable to human influence on the climate. So basically, it's unlikely we would have seen this trend had it not been for the way that humans are influencing the climate. So we basically we updated this with some new data, and I'll come to the results in a minute. Then to combine these pieces of information, because we have kind of two different scales. Here you can see grid cells, and in the named entity recognition we have entities basically. So here we have the province of the White Nile, or we have the city of Khartoum, and all of these are entities of different sizes. And what we do is we map these entities onto grid cells. And if one study talks about an entity that's in one grid cell, then we say that this grid cell has one study talking about it. And if a study is talking about an area with two grid cells, then we say that each of those grid cells has half of a study talking about it. So we basically distribute the studies across the grid cells that contain the geographical entity that the study discusses. So that's how we do that part. And the other way around, we may want to talk about an entity like Sudan. And so we have different, in each of the grid cells, we have different temperature attribution categories. So we can say that 74% of the grid cells here display an attributable trend, warming trend. And of course, it's more precise to say, to talk about the area, because grid cells are all different sizes, but this is just for illustration. Because grid cells in the northern latitudes are smaller than grid cells in the northern and southern latitudes are smaller than around the equator. Okay, so how did our model do? So first, in terms of the inclusion, so the first task was, is this about climate impacts, observed climate impacts or not? And actually this was, the performance metrics here aren't super impressive because it was actually a really quite difficult task also for humans. But what we did find is, at least as compared to support vector machines, that using transformer-based approaches did have a really quite large improvement in performance. And we weren't actually sure. We hadn't before this paper, we hadn't been using transformers, and we weren't really sure, will this work for our data when we have relatively small data set sizes? I don't know, is it worth the extra effort? But in actual fact, it was really a huge increase in performance. But what we did find was that in distinguishing between the different types of impacts, then machine learning was really good at this task. So to say whether something was in coastal and marine ecosystems, or human and managed systems, or in mountain, snow, and ice, rivers, lakes, and soil moisture, or terrestrial ecosystems. And these are the categories that we had at the beginning with the IPCC. This is the way they kind of categorize different types of climate impacts. And we were pretty good at distinguishing between these. There were some particularly tricky examples, like everything to do with salmon was super confusing, both for the humans and the machines, because salmon go between freshwater and marine ecosystems. And so deciding which, if salmon are affected by climate change, then deciding which system is affected is really complicated. And often the machine learning algorithm, you could see when we looked at the kind of errors that were coming, the machine learning algorithm would think, okay, fish, so marine, but you could see the kind of shortcuts that were, that we think were accounting for some of the false positives. Also with precipitation and temperature, we were rather good at deciding whether it was precipitation or temperature that was driving the impacts in these different systems. So what we found to describe what these results, so making them predictions on the rest of the data that we hadn't labeled, we found about 100,000 studies, plus and minus quite a large amount, that are relevant to the observed impacts of climate change. And these were kind of distributed across the different classes and the different continents. And I'll come to the ways that these distributions are in even a little bit later. But we had lots of stuff on terrestrial ecosystems, a bit less on some of the others. And if we plot this onto a map, we can show the kind of density of studies per grid cell. So this is back to what I showed before about distributing the study across the grid cells, because otherwise, if we have lots of studies on Russia, but if we make every grid cell in Russia darker by one, then of course the big countries will have more evidence, but actually in practice, this is distributed across a large area. But we kind of see what we'd expect, that in Europe and in North America, we have really high concentrations of evidence, also in India, and also in China and East Asia. And if we control for population, then actually Australasia has the largest amount of evidence on climate impacts per population per capita. We also see some interesting differences in the kind of share of different systems for which we have evidence on. So in North America, for example, and also in Europe, we have lots of evidence on terrestrial ecosystems, whereas for Africa, this is almost equal with human and managed systems. So in Africa, we're studying the effects on human systems much more than at a much greater percentage than in greater proportion is on human and managed systems than in North America and Europe. And this isn't trying to say where are there climate impacts, but really where do we have evidence on them? And we have a very strong hypothesis that these two things are not exactly the same. So we want to kind of tease that out a little bit by looking at the evidence of where we know the climate has changed objectively from the observational data. So this is what we get here when we look at the updated detection and attribution results. And here we see all of the red cells here are areas where the change in temperature is attributable to human influence on the climate. And as you can see, this is pretty much the whole world. So this kind of generated a quite striking finding that basically everywhere is already affected by anthropogenic climate change. And basically, compared to Tom Knudsen's work that was about 5 years ago, all of the kind of gaps that we had, apart from where we have missing data in some areas in continental Africa, almost all of the gaps that we had where we weren't sure, we knew it was warming, but we couldn't say for sure whether this was to do with human influence on the climate. These have all closed in the past 5 years. So for temperature, almost everywhere we can say that human influence on the climate has caused changes, warming trends. With precipitation, it's much smaller areas, and it's also much more tricky because also the things can go in both directions, and the relationship is much more complicated. So we can say less about precipitation. So to bring these two strands together, as I suggested, we kind of merge everything into one big graph that's a little bit hard to read. So I'll try to explain it as best as I can. So these top two boxes here, these contribute to the hue of the bottom one. So basically, anything that's pink or purple is an area where, for either temperature or precipitation, the trends since 1951 can be attributed to human influence on the climate. And the intensity of the color describes where how much evidence we have on how those trends have affected other systems. So basically, we know it's got hotter. How many studies do we have showing us how that heating has contributed to impacts in terrestrial ecosystems or human influence on the climate, or human systems, sorry. And basically what we see is that it's pink almost everywhere, but it's dark pink in areas where there are high research budgets, basically. So we can say that we would expect that there will be impacts here, but we can describe this as a gap, because we know that actually it has got hotter, but we have little evidence describing the effects on other systems. And as I kind of pointed to earlier, that there are some systems that are not being studied as intensively as they would be in North America or Europe, for example. And if we kind of sum these areas by population, then basically 85% of people live in an area where there is an attributable trend in either temperature or precipitation. Almost all of those actually live in an area where, so for high income countries, almost all of those live in an area where there are many studies talking about the effects of those trends, whereas in low income countries, also the vast majority live in areas where there are attributable trends. The slightly lower proportion is because there are larger areas with data gaps. But of these people, there are many more living in areas where there is little evidence about the effects of this in other systems. Okay, so to conclude, we managed to identify a large body of evidence about climate impacts, so really very, very large, emphasizing what we have seen recently in various kind of pieces of anecdotal evidence and disasters and all kinds of things, heat waves. And it underlines in another way, and many people have demonstrated this in various different ways, that we are already feeling the effects of climate change. And as I was trying to say before, that I think what we know about the effects of a changing climate on human and natural systems is dependent on where we live. So some people have access to more, or some people are living in areas that are more researched in terms of how climate change is affecting other things. Some caveats to this study: that the current results only show studies in Web of Science and Scopus, and there are other literature databases. So we definitely miss out some relevant stuff. Our query probably misses out some relevant stuff as well. And also that the study identification is approximate and uncertain, although we can account for this uncertainty to a certain extent. And also that geoparsing is really inexact and tricky. So if a study talks about Western China, then we can extract the entity China, but Western China, we can't, unless it's a particular region, we can't attribute it to those, the the grid cells on the left-hand side on the map or anything like that. That's beyond what we're able to do. Yeah, so that's pretty much it from me. And I'll just go to the next slide where there are a couple of resources. So basically all the code is on there. There's also a nice interactive map we made, so where we can see these graphs, but where you can hover over the different grid cells and look at the different values with different parameters and all those kinds of things. And then there I would finish it, and thank you for your attention. And I look forward to any questions you have. Thanks a lot.
Yeah, thank you for your presentation, Max. Thank you so much. So many visualizations in the talk. That's really great to see, and I can only double down on that. Everybody should try out these maps, these interactive maps. If you have any questions, you can write them in the chat, and I will read them out. Or if you want to, you can also raise your hand and speak up. Any questions so far? Okay, if there are no questions from the audience, I definitely have one. So you showed as an NLP model that you used transformers for the first time, right? And you said Distilbert was the model that you used. So I was wondering whether you can assess how your research results would change with improving on these models. So let's say you do this research now again, or maybe in 1 year again, language models become more powerful. Do you think the maps will look different?
Yeah, it's a good question. And it also reminds me, I should also point to one other nice thing that's changed is some people have produced a version of Distil Roberta that has done additional pre-training on climate relevant corpus. And I think that in another project we're starting to have a look at. And I think in general, there we just assessed transformer based versus not. And I think it would be interesting here to look at the different types of models. And I think we would get better performance. I think we would have smaller uncertainty ranges. I don't think the numbers would be vastly different, at least I hope not. And I think qualitatively, the results would stay pretty similar in terms of the distribution of evidence. I think it's unlikely that that would change. And also partly because these findings kind of corroborate hypotheses that we already have and what we already know anecdotally about the literature.
Yeah, thank you. There was one question from the audience about how these findings are now being used. Maybe you can say something about that, the very first question in the chat.
Yeah. So at the moment, I think only the headline findings are being used in the sense that it's useful to have another way to say climate change is happening. And I think that's every way that we can say that is useful, although we can say it in really many ways. But actually, I think there's much more useful data in there. And I think in the interactive maps that we've already built, they're kind of interesting and you can scroll around a little bit, but what would be super interesting would be to be able to say, okay, I'm interested in these grid cells and I'm interested in this time period, or I'm interested in this type of impact. Show me the studies that are relevant here. And that's something that we're kind of in the process of building as part of another project. And I think, yeah, this would be super useful because in the end, to some extent, you could say, well, why do you need to use machine learning to estimate how many studies there are of different types? I think there would be actually simpler ways to do that. But I think what we care about is which of those studies are actually relevant to those different things, because then in principle, then we can use those studies to do further and more detailed knowledge synthesis. But that's in progress, I would say.
Yeah, there's technical question about your approach regarding hyperparameter optimization. So Malte asked here what parameters you optimized and which of those had the biggest influence on the results.
Yeah, that's a good question. And I should try to remember. We used the ones that were mentioned in the BERT paper and the parameter space that was also mentioned in the BERT paper. And to be honest, we didn't look at what drove variation in performance. So I can't actually tell you which ones. And actually that would be a useful thing to do because the search procedure was expensive, computationally expensive. And I think it would be to have kind of heuristics about which kind of area of space to focus on would be a much better use of resources than simply searching the whole thing. So yeah, I think in the future work, we'll probably try to dig into that a little bit more.
Okay, so then there's a question by Yuri in the chat. I can just read it out. Can you assign geographical mentions to regions like provinces or districts rather than grids? Would that give better precision?
Mm-hmm. I'm not sure what you mean by precision here. So I mean, first we have we just use a named entity extraction library. We use Mordecai. I don't know if you're familiar with that one because it also does the geo. It doesn't just give you the text and the entity, but also the kind of geo name, so the kind of geographical entity that is predicted to be referring to. And so we have those, and in some contexts we can use those, but if we want to talk about stuff related to the grid cells, and also we have these on different, each of these are kind of different on different scales. So some are countries and some are districts and some are parks and some are oceans and some are deserts and some are mountains, and all of these different scales. And we go through a big process of going through searching for shape files which match these things. So using the Natural Earth shapefile libraries, where we have libraries for all these different things. So physical features, administrative units. We go through all of these, and mapping to grid cells is a way of having one kind of common scale that we can kind of consolidate into. I think the other option would be to go by, no, that would also be tricky, to go by country, but then not everything is in a country, because sometimes you have a desert which is across two countries, or you have part of the ocean, or so actually, yeah, it was quite complicated, and using grid cells seemed like the simplest thing at the time. Also because then it allowed us to compare with the observational data that we had about the temperature and precipitation trends in those.
And then there's a question, I think, which is a bit more in direction of future work by Ahmad. So in the chat, the last one. And the question is whether you thought about using the full text data from relevant papers, from climate research papers, right? And compare their conclusions and see whether they contradict each other or whether they are aligned and come to the same conclusions, things like that.
Yeah, I mean, that would be super interesting, I think. It's way beyond what we did, I think. In the end, what we did was really simple. We just labeled some data, and each document had a label and or a number of labels, and we tried to predict those labels. And this is a really kind of nicely discrete task. It was quite hard to generate the labels consistently. It's quite hard to learn these labels, but yeah, it was kind of manageable at least. I think understanding which papers have the same conclusions, I would struggle to think of how to label that. I think that the labeling task would be quite complicated, and also the learning approach would be tricky. And another thing is that we use the abstracts of the papers because we're looking at which papers are about which things. But getting the full text is also complicated, and getting the full text in a nice format is also complicated. And I think there are certain databases where you can get full text, but then if you only get, I think most of them only have, and this is something we're exploring a little bit at the moment, but a lot of them only have a subset of all of the full text that exists. And if that subset is non-random, then that brings in some other problems. And yeah, it's tricky. Full text are really quite a tricky thing. But I think there are really interesting questions, and also there are people working on stuff like this. So especially in health, for example, I think there are lots of effort going into things like this. But I think it would help to have also a more defined and more discrete research question as well, because I think, so in health, for example, you often we look at the effect of meta studies that look at the effect of treatment X on outcome Y. And there, I think it's more reasonable to expect an automated approach to understanding if the conclusions are the same. But if our kind of topic is as broad as what evidence do we have on observed climate impacts, just in general, and we were dealing with loads of different disciplines, loads of different types of impacts, I think we could do that at this scale. So maybe on a kind of more tightly focused research question, stuff like that might work. But yeah, it was super interesting. It would be, definitely.
Yeah, definitely. Yeah. Then again, thank you so much for your talk about applied sustainability research. I think it was a very inspiring closing words for this first part of the session today. If more questions come up in the chat, maybe you can answer them also in the chat. And yeah, we continue with the second talk, I'd say. All right, then let's do that. Okay, then I invite our second speaker to start sharing his screen. Vladimir is going to talk about generative question answering with LFQA. And Vladimir is a long-time open search contributor to Haystack, the framework where now also LFQA is implemented thanks to him. And he recently joined deepset as a senior software engineer. I'm super happy about that. And now very much looking forward to your talk, Vladimir. Stage is yours. So we can already see your screen.
Yes, I unmuted myself.
All right. So stage is yours. Go ahead.
All right. Thank you. Hello, everyone. We have a lot of ground to cover in a very limited time, so I'll jump straight into the agenda. So in outline, what we're going to cover today. I might speak a bit faster than usual, but if you give me your complete attention for the next 25 minutes, you'll come out of this presentation knowing pretty much everything about LFQA. So let's move right on. In the first 9 to 10 minutes, we'll look at the history of QA systems, motivation for their existence, and the general system architecture. We'll then look at the issues identified after the first LFQA transformer-based systems were released, how we addressed these issues, resulting in a new data set and a set of new LFQA models. And we'll look at the current, most recent state-of-the-art systems. And finally, we'll conclude with a brief demo of Wikipedia Assistant. Before we dive straight into the LFQA, it's worth to pay homage to some of the early QA systems, and for two reasons. The first one is to understand how long we've tried to build these systems, and second, to appreciate how far we've come from these humble beginnings. ELIZA was created by Professor Weizenbaum at MIT in the 60s, and it simulated conversation by using pattern matching and substitutions that gave users an illusions of understanding. Even Weizenbaum's secretary gave ELIZA human-like capabilities for feeling and understanding. Now, I don't know if you've been following the latest news about Lambda, but the echoes of ELIZA certainly can be heard today. Sherdlu was developed by Terry Winograd at MIT again in the late 60s. And in this program, as you can see in the bottom left corner, A user carried conversations with the computer, instructing it to move objects and naming collections of objects and querying the state of this simplified block world. Watson was released by IBM, was released in 2011. It was a system capable of answering questions posed in natural language, trained on the answers generations in the game of Jeopardy. And as you know, Watson was the first program to beat human competitors by a large margin. Another recent architecture that I want to mention is BiDAF, that you can see in the right-hand side. It was released in 2017, and it stands for the Bidirectional Attention Flow Network. And you can see by the sketch of this network that it bears a lot of resemblance to the modern transformer encoder-decoder architectures that we are familiar with today. Finally, as we all know, BERT was released in November of 2018, leading us into this transformer revolution that we live in today. So having looked at the history of QA systems, I want to quickly touch upon the QA system classification. And there are a couple of verticals of how other people organize and think about them. The most common one that I found was that the vertical of classification where we are concerned about how the answers are actually created. And by this classification, we have extractive QA and abstractive or generative QA. The best way to think about extractive QA is through an example. So in this example, we see that a small text about factual information about Germany, and given a question of what is the capital of Germany, a system is able to easily extract the word span Berlin. In the abstractive generative QA is a bit different, where it's not as simple as the extractive method, where this system is actually generating synthetic original answers given a question and the retrieved context paragraphs. Another way we can divide these systems, we look at these systems are by the question where the answers come from. And in this case, we can think of them as an extrinsic QA systems, where the answer is actually taken outside of the model. Model is allowed to look at the other resources, reference other resources in search for the answers, while in intrinsic QA systems, there is no context provided, and the answer is completely generated by the model itself. LFQA, the subject of this presentation, is an abstractive generative extrinsic QA systems, and we'll look at the data set, the architectures, and the issues that were identified that served also as a motivation for my contribution to the field. Speaking of motivation, let's look at the main driving forces for the LFQA's existence. And as you have seen, we humans have been fascinated by these systems for at least 60 years. And they're not confined to the MIT AI labs anymore, but they're becoming omnipresent of course, in the form of search engines. And in the past, these search engines provided website recommendations instead of direct answers. But recently, and I don't know if you noticed this, if you pose a question in Google, it will attempt to answer it directly. As in this case, for the question, what is contrastive learning in NLP? Google used the extractive approach to answer my question directly. So, and this is just the start where I think we are going. I mean, in the future, where QA systems will provide the direct answers to most of our questions. And this is also my main motivation for research and focus on this subfield of question and answering, as I'm convinced that the search engines in the current form, where they simply provide search results, will transition into QA agents that will answer our questions directly while citing references used in crafting those answers. All right, so as the Transformers revolution started, the first big foray into LFQA happened at Facebook Research Lab in 2019, the next year, led by Angela Fan and Yosine Yonite, a team from Facebook, NYU, and Google jointly created the LE5 dataset. If you are not familiar with Reddit forum, this forum basically consists of various questions, as you can see on this slide, posed by users expecting digestible answers to sometimes admittedly complicated questions. Angela's team not only released this data set, but they also a model to encode questions and passages, and another model based on then recently released BART architecture was fine-tuned to generate answers given a question and found context passages. Demo of this model is available on Yasina Yernite's GitHub page. Normally, the question arises, how good were these first transformers-based LFQA systems? Some of the answers were good. There were some model hallucinations, and some answers were plain wrong. But overall, it was far from human performance, as human evaluators preferred gold responses from LE5 dataset in over 86% of the cases. Okay, moving on to the LFQA architecture. And here we'll focus on two parts of the architecture. The first one consists of the document store and the retriever. And the second one is related to abstractive generator. And let's look at them in turn. And along the way, we'll describe the entire process of the answer generation. First of all, as you may have guessed, we need to fill up our document store with the relevant documents that we'll use. And in this case, we used Wikipedia paragraphs, but I mean, they don't have to be. They could be, say, corporate documents from your intranet or something similar. After importing our documents, we'll create the embeddings and embedding representations for our questions and paragraphs. And in the case of Wikipedia, there are over 20 million of these paragraphs. So if one can embed the entire Wikipedia, it's likely that it can handle your use case as well. Second, we'll connect this abstractive generator model to our system, and then we'll pass a query and the retrieved context passages to the generator model that will then generate the original answer. So let's double click on this process where we select these paragraphs. And here we have a simplified vector representation of our passages and questions, which is flattened from this multi-dimensional embedding space into a two-dimensional space. And we've done this simplification for the purpose of just conveying the message of how query embedding in this case is likely going to be close to the most semantically relevant paragraphs. And these are actual paragraphs from Wikipedia. Here is where the retriever model will select the top K most relevant paragraphs, in this case, probably these two on the left, from the vector database. Finally, once we have retrieved the top K most relevant context paragraphs, we'll pass them along with a query to the generator model. And the generators are these text-to-text encoder-decoder models. And I know it's hard to remember all of these if you're not intimately familiar with NLP architectures, but think of these models as translation models that are fine-tuned on answer generation instead of translations. And the generators take query and retrieve context as input and use them to generate the output, the answer. Okay, now it's time to move on the first issues identified in these first transformer-based LFQA models. And if there's one paper one research paper to read about LFQA and nothing else, I would readily recommend Hurdles to Progress in Long-Form Question Answering by Kalpesh Krishna, who was a graduate student at the time, his supervisor, and Aurko Roy from Google. And three of them have done some amazing and eye-opening experiments leading to biggest leaps in understanding of LFQA. Well, first of all, they discovered that the generated answers are not actually grounded in retrieved documents. In their ablation studies, they replaced retrieved documents with random documents, thus conditioning this generator with random paragraphs. Surprisingly, they didn't notice a lot of decline in quality of the generated answers. So something was seriously amiss here. Second, LE5, they found that LE5 has a significant train validation overlap, and that at least 81% of the LE5 validation questions occur in some paraphrased form in the training set. And as you know, validation set is used to let us know when we have to stop training. The idea is that you check your model performance from time to time, and when there seems to be no more improvement, you stop the training. Well, what if your train and validation sets are basically paraphrases of each other? The model performance is going to be estimated too high. The third conclusion they made is that the Rouge L is not appropriate metric for generated answer quality. And I think that Angela Fan and Yassine in their first paper chose to, in their first attempt to generate these LFQA models, used Rouge for the lack of any other metric that existed at the time. If you don't know, Rouge is used for machine translation evaluation. But if you think about it, Rouge is not appropriate for these kind of is not appropriate metric for this kind of generations, because I mean, if you ask a question, what causes a traffic jam, one could use many analogies to explain the cause of a traffic jam, and answer space is so unconstrained that this n-gram overlap metric that measures the gold references against the generated answers is simply not appropriate, which leads us to the last conclusion that Krishna and his colleagues made, is that the human evaluation is challenging but necessary for evaluating of LFQA. And we'll soon see how researchers from OpenAI trained models based on human preferences that were actually able to achieve the objective, but of course without significant cost of using human evaluators. Krishna and Roy concluded their paper by saying that the main reason for answer generations not being grounded in retrievals is a large train validation overlap in LE5, and that any further research should start from there. Well, after reading this paper last year, I reached out to Yassine to ask him if he wanted to address some of these issues, and he readily responded by saying that he was working on some unrelated research and that he will be glad to supervise me if I wanted to. And that's how we started work on a new LFQA dataset and a new set of models for LFQA. Okay, so how we started? We started first by confirming Krishna's findings. We, aside from looking at dozens and dozens of these examples, we started by looking at the overlap between the train set and train validation and test set, and with using this sentence birth transformer. And the range of distribution of this similarity is depicted on this slide. So they range from the paraphrases of each other in the top row all the way to the bottom, to the completely unrelated questions. And I included this slide so you can just get a better sense of similarity. And I want to point out to the third question here, which both of them are related to a question about crying, but they're completely different. Yet the similarity here is close to 0.7. Okay, so we started with the objective of creating a new LFQA dataset with train validation tests splits such that all three subreddits are equally represented in the all of the splits, and we used Explain It Like I'm 5, Ask Historians, and Ask Science Reddit forums. We set the goal to create a new data set with the train validation test overlap being minimized while maintaining this, the data set size compared to the old LE5 data set. Validation and test splits contain the LE5 test validation examples from the knowledge intensive language task version of the dataset, and this is mainly for the reason so other researchers can use this dataset and compare it to the old one. And the last objective was that the validation and test splits included the questions from high Reddit scores. Okay, so how did we achieve this? First, all candidate questions were hierarchically clustered using the certain merge similarity threshold, and we use the threshold similarity of 0.83 as a cutoff value, which seemed to give us the best trade-off. We wanted to have a data set large enough in this size similar to the old, while minimizing the overlap at the same time. And the best visualization of this overlap is the probability of overlap distribution in the question in the train and validation sets. If you look at the left-hand side of this slide, of this graph, we'll see the before kind of a state of the LE5 data set, where the probability of overlap centered around 0.8 similarity. Again, here confirming the Krishna's findings, where the right tail was even at 1.0 similarity, basically paraphrases of each other. And we moved this at the end result was the LFQA data set on the right-hand side that had a minimized this overlap. As you can see, the distribution is very narrow, but also shifted to the left or to the smaller cosine similarity. Then we use this after creating this new LFQA data set. We created we trained a set of dense passage retrievers based on it, along with a BART-based abstractive generative model. And all three of these models are available on Hugging Face Hub. As a crowning achievement of this experiment, we also made a Wikipedia assistant Hugging Face space, which we'll demo shortly. Okay, so now that we have looked at the new data set and the new models, it's time to look at the current state of the art and what's coming, most likely coming in the near future. So how can we mention LFQA without touching up on WebGPT? That was created by researchers at OpenAI, who asked themselves if there's something about this process of browser search and the answer synthesis, and they wondered if machines could do that instead of us. So they replicated the human browser use by using a technique, a reinforcement learning technique called behavior cloning. And behavior cloning model represented the baseline model. Now, remember how Krishna drew attention to a need for human answer evaluations. Well, John Schulman and his team at OpenAI replicated human evaluations by creating a special model that learns to predict which answers humans would prefer. And then they optimized the first model against this model by using proximal policy optimization. The results were absolutely stunning, and it was the first model that whose generations surpassed human performance, and the answer generations of this model were preferred 56% of the time to the answers crafted by human volunteers. I want to briefly look at the research in academia, where there's a recent trend that involves mixing knowledge graphs and language models. And it's based on an insight that answering these complex questions about textual narratives requires reasoning over both a stated context and the world knowledge that underlies it. However, language models do not robustly represent latent relationships between these concepts, which is necessary for reasoning. And one of these models is GREASE-LM, which was released about 4 months ago by a team from Stanford University, and it uses so-called closed common sense reasoning. And it's called closed because it's actually trained on multiple choice rather than the one that's more interesting to us, which has open-ended answers. And GREASE-LM is interesting because it fuses these encoded representations from pre-trained language models and the graph neural networks over multiple layers, as you can see on this right-hand side, multiple layers of this modality interactions. So what happens here is that information from both modalities propagates to one another, allowing language context representations to be grounded by structured world knowledge, while at the same time allowing the linguistic nuances like negation, hedging in the context to inform the graph representations of knowledge. And the last model that I want to briefly look at is Dr. Fact by researchers from University of Southern California and Google Research. And the authors propose a open-ended common sense reasoning, OpenCSR, the task of answering a common sense questions without any predefined choices. So not multiple choice, but the actual one that's useful in the real world. And this is very challenging, as you know, due to large decision space and because many questions require this multi-hop reasoning. And the best way to think about it is by the example on the top, where the question is, what can help alleviate global warming? So in this case, we follow a tree of facts where actually it starts with a tree that removes the carbon dioxide from atmosphere. And then there's another fact where carbon dioxide is the major greenhouse gas, then in turn contributes to global warming. So by multi-hop following these facts, we can conclude that trees do indeed alleviate global warming as a part of the answer. Okay, so just as a concluding remark, I want to mention that although these systems from research are super interesting, and I also participated in implementation of importing of the GREASE-LM to Hugging Face, one has to take a note that all of these attempts that mimic human thinking and use high-level human-crafted kind of heuristics have failed in the past. And any time that humans have attempted to encode their knowledge into programs like chess or game of Go or speech recognition failed, while the general methods that leverage computations are ultimately most effective and by a large margin. And if you're interested in this domain, I highly recommend to read a small essay by Richard Sutton called The Bitter Lessons in AI. Okay, so now it's time for the most interesting part, which is the demo of Wikipedia Assistant. Okay, so let me go to the Wikipedia Assistant, which is a Hugging Face space available under the deepset org, and the answer generation usually takes about 20 to 30 seconds, but I prepared about 4 or 5 questions that are now cached, so you can get a sense of how everything works. So the question that has followed us throughout this presentation: why do airplanes leave contrails in the sky? We'll ask it now. All right, so we get a very interesting, legible, seems correct answer that describes this process in 2 sentences. I want to guide your attention to these bubbles, and they range in the color from red to green, or values from 0 to 1, and they represent the grounding. So the greener these bubbles, it means that the sentence, like in this case, the second sentence of this answer is better grounded than the first one. And We'll get back to that. And below we have context and context paragraphs that were retrieved from Wikipedia that were used, as you remember, in a generation of this answer. So there are 3 or 4, I think we used top K4 in this hyperparameter setting here. But the more interesting way to look at these paragraphs is by answer similarity. And this way, each sentence from an answer is isolated here along with the top K3 of the most similar sentences that we use to estimate the grounding, where the actual answer sentence came from. So that's also an interesting way to play when you get to play with this demo, to look at these answers. So let's look briefly at a couple of other questions. The second one I looked at was, and these are all questions from LE5, from validation and test set. So this one is about Pope, and it produces a pretty legible answer by it, where the Pope is the leader of Catholic Church. He's the head of Roman Curia. And you can also see that all of the sentences have a very high grounding by these bubbles that are quite green in this case as well. Let's look at this example this example about crying that we had previously. Again, the first sentence is a bit iffy, but if you notice, this last sentence has a grounding of 1. So this sometimes also happens, that entire sentence is almost ripped off completely from a context paragraph and kind of put as a piece of a puzzle of an answer to complete the answer. And the last example that I want to show you is this example that I've noticed has a very low grounding, and also a question from validation or test set, which its question is about Mali in Africa and what do Germany and France have to do with it. And the answer provided is a bit longer, but you can see that all of the sentences have this kind of a very low grounding, and I know this specific one of 0.2 states that these two groups have been fighting each other for a long time, and MNA has been fighting them for a very long time as well. It sort of doesn't make too much sense, but answer overall seems to be related to Mali and Mali National Army and all of the troubles that are happening in this part of Africa. Okay, so I think this concludes our demo. Of course, please try it yourself. I think that if you look for it in the spaces, it's easy to find. Okay, 1 second. Yeah, if you go here by sorted by most likes, I think we're in the top 10 Hugging Face spaces. So if you like it, please don't hesitate to give us a heart as well. Okay, so if you feel shy to ask questions now, you're always more than welcome to contact me at my email directly with additional questions that you might have, or perhaps some suggestions of how to improve these systems, and even research proposals that we might collaborate. And with this, I hand it back to you, Julian.
Yeah, thank you so much for your talk, and thank you for sharing the demo with us and demonstrating how LFQA works here. Super interesting. Let's see if there are any questions in the audience. Again, either you write them down in the chat, or you can speak up. Raise your hand and speak up. So there is a question in the chat already, right? Mm-hmm. So Sebastian asked, how do you think that image, speech, video will play a role in the future of LFQA? So asking about multimodal.
That's a really good question. And in my correspondence with John Schulman, he basically hinted on this direction well, not explicitly, but he said we'll use other modalities in the future versions of WebGPT. So I definitely think that this is coming.
I see Max raised his hand. Max, go ahead.
Yeah, thanks very much. It's a really interesting presentation.
Thank you.
I'm really interested in the way that we go about evaluating such tasks, because you said that humans preferred these answers, but somehow that doesn't capture whether those answers are better or not necessarily, because I think one of the things that's super interesting with these techniques, and especially when they're used in search engines, and some people have presented some examples where there are dangerous or wrong answers. So how do we, what if we prefer answers that are wrong, or that we prefer answers that are misleading, or we prefer answers that are biased? How do we deal with that as an evaluation challenge?
That's a great point, because previously researchers have tried to use all of these various metrics. So one of them was reveal one sentence at a time and see if you fool humans. So that was one approach. There was another approach to check the factual correctness, but it seems like this approach that OpenAI took of crafting a specific model, and it's a very interesting and approach of how they did it, because they let the model generate two answers, and then they ask a human, well, which one of these do you prefer? And then they backpropagated the loss on these preferences that humans made, and that's how they crafted. And I think they used, I forgot how, but I think it's an order of 10,000 of these comparisons, but I have to check that number. So far, that's the best approach that I know of, but probably there's going to be more approaches that would probably check the factual correctness. And one of the things that I forgot to mention while we were at WebGPT, it did not perform at human level on trick questions. So there are specific data sets. One of them is called Truthful QA, which is an adversarial data set that has questions like, what happens if you break a mirror? And model is likely going to find an answer that you'll have 7 years of bad luck or something like that. So on that set, WebGPT was short of human performance. I mean, it's not a direct answer to your question, but hopefully it gives you some sort of a sense of what's going on in this area.
Yeah, coming to trick questions, I think maybe you can share the demo again, because there was a request in the chat to try out one more question, and it should be cached now already.
Oh, okay.
So maybe you can just share your demo and the screen again, so that everybody sees it, and then try the question. Yeah, sure. So the question is also in the chat.
Let's try it.
The question is, how many times has Egypt crossed the Golden Gate Bridge?
Wait, where is this?
In the
Aha, okay.
And the screen that you're sharing right now is yeah, there.
Okay, sorry, I have all these windows popping up.
Yeah. So the question was what you would say about this. I mean, especially like the third sentence, I think it is a bit funny. And then there's also a follow-up question on the chat by Patrick. Similarly, right, the question is, does the model make up answers from time to time, or can it tell you, I don't know? So
well, not yet, of course, not yet. I mean, this is, well, it does, it assumes that the question is not adversarial, as in this case. So, I mean, it picks up whatever it finds in the context messages, right? So let's look at what it found. It found something about Golden Gate Transit, right? Mackinac Bridge, Rod Al Farag Bridge was over Nile River. So it's mixing up Cairo and San Francisco in this case. So yes, absolutely, the model was fooled in this example. Although it seems like it provides answers that are legitimate and correct. But because the question was adversarial, of course, the answer is not right.
Thanks. Funny example, I think. And
Yeah.
we also have now identified a topic for future work, making these models able to tell when they don't know the answer.
Yeah, absolutely. I mean, this is a hard problem. I mean, if OpenAI cannot solve it, then imagine how hard it is.
Any other questions from the audience? Okay, if there are no further questions, I mean, you can ask anything about LFQA. Vladimir promised that you will learn all about it in these 25 minutes. So,
well, there are some new messages in the chat. Oh, okay. Thank you, Jasper. If you feel a bit shy to ask here in front of everyone, please reach out to me and ask a question. Of course, play with the Wikipedia assistant, and any feedback you have is also very valuable.
all right, then I'd say with that, we close this part of tonight's meetup event. I'll stop the recording and then we'll head on to the Zoom breakout rooms. So I'll stop the recording.